difference. Now, the good thing about finite difference is that it is ideal in a scenario where you have access to the equations. If you don't have if the black box is available, you cannot do this. You can use shooting method. But if the equations are available to you, in many cases they are, then you can use this method. So what this method does is it writes. So here's the steps. A, rewrite the ODE using finite difference. Right? An ODE is what? It's basically a differential equation. We've learned how to write approximation for dy by dx using some of the early part in the course. We had forward difference, central difference, and so on. So use that. Once you do that, second step is assume unknowns at grid points. Okay, so how does finite difference work? Well, if you want to find dy dx, you say yi plus 1 minus yi divided by delta x. So those yi plus 1 yi values at grid points. So those are going to be your unknowns. You treat them as unknowns, and that's what it is. So this is, if you have dy dx is yi plus 1 minus yi divided by, usually delta x is given to you, then yi y are unknowns. So you'll treat them as unknowns, something which you will solve for later on. And this will probably be, this look very odd right now, but once I solve it, trust me, you'll understand what I mean by step 2. Now then set up equations based on boundary conditions. And then third step is solve for unknowns. Okay, so this has got a flavor of some of the things we've done before. If you remember curve fitting, in curve fitting, we basically wrote down an equation of n constants. So quadratic equation, we had 3 constants. And then to solve for those 3 constants, we had 3 conditions. This is similar. Instead of having constants like the way we had of polynomials, coefficients of polynomials, here the constants are basically these. These are the unknowns. Okay, and then if you have unknowns, how do you solve them? Well, you need to set up some equations. Those are set up using boundary conditions. Okay, so once you set it up, the step D is trivial. At least for the problem we'll be doing, it will be trivial, but D usually can become non-trivial. This could involve root finding. If the equations are linear, then it's linear algebra, ax equals b. We've done that too. But if the equations are non-linear, they have squares or exponentials, anything other than linear, then you could use root finding. So again, methods are Newton, Raphson, secant, and so on. Okay, so for problem solving, we just use the simplest problem, which is going to be linear. Okay, so it turns out that the problem I chose, which is the same problem as the one I did before, will give us linear equations. Okay, so here we go. Let's do the same problem. Copy. Okay, if you want to write notes, then you can just say same problem, but solve using finite difference. So use finite difference. That's the only change. Yeah, I might want to say here, use forward difference. Let's see. Yeah, so it will be a little different. You can use with forward. Okay, note one of them uses differentiation, that this one uses forward difference. That's a different thing altogether. Okay, so let's see how to solve this. Okay, so uh, x equals 0, 0 0.1, 0 0.2, 0 0.3, 0 0.4, 0 0.5. Okay, y values. Now this is where the method will differ. In case of shooting method, y0 was the unknown, but here we'll create more unknowns. y1, y2, y3, y4, and y5, by the way, is known. It's just 1. So these are going to be my unknowns. Okay. Okay, now let me use forward difference. So let's take this equation and write it as a forward difference divided by delta x equals minus xi yi. Okay, so when I simplify this, I get yi plus 1 equals 1 minus delta xi. So delta x times xi yi. So the equation looks exactly identical to Euler's integration. It's no wonder because I use forward difference. Now, if you use any other method like central difference or backward difference, the formula will look slightly different. Okay, so at this point, you could say it'll just be the shooting method. Well, in this trivial example, yes, that's true. But in the true spirit of finite difference, let me show you how this is solved, assuming that it was much more complicated than this, and you maybe had, I don't know, central difference, something like that. So let's see how to solve it using this equation. So let's take this equation, and I will start writing. So this is, let me correlate this with what we have here. So first step, using finite difference, step A, this was step A, okay? This one was the second part, B. We actually, it was embedded here. This is, we did it a little bit earlier, but it'll again show up again. So that's step B. Step B will show up again when we try to write this down. So here's the step, well, here, yeah, step B, you could do it either way, unless you, you could have done that after A also. I mean, it doesn't really matter in this case. Now, C, however, has to be done only after you do A and B. You cannot escape that. Let's see how to do C. So C is basically taking this equation here and then writing it as multiple equations. Let's just take that. Okay, so here we go. I equals 0. We have y1 equals 1 minus 0 0.1 times 0, y0. So it's y0. I equals 1. Y2 equals 1 minus 0 0.1, 0 0.1, y1. So that comes out to be 0.99 y1. Next, we take I equals 2, y3 equals 1 minus 0.1 times 0 0.2, y2, 0.98, y2. I equals 3, y4. I'm just using this formula, by the way, repeatedly. 1 minus 0 0.1, 0 0.3, y3, 0.97, y3. I equals 4, y5, which is, by the way, 1 equals 1 minus 0 0.1, 0 0.4, y3, sorry, y4. 0.96 y4. Okay, so I'll rewrite all these equations in a way that we can use matrix manipulation to solve them. So the first equation is, okay, I'll move the y0 on the other side. So we have minus y0 plus y1 equals 0, the first equation. Second one, we have y1, y2. So I'll write it in this specific way, which will help me later on. 0.99 y1 plus y2 equal to 0, the second equation. Third one, we have 0.98 minus 0.98 y2. It's negative because I moved it on the other side, plus y3 equals 0. Then we have 0.97 y3 plus y4 equals 0. And the last one is 0.96 y4 equals 1, right? 1 is number here, goes here. Okay, so you can see that it's basically a linear equation. All the lines are linear. We'll just write it as a matrix now. It's best for me to copy this. Okay, so here it is. Okay, what I need here is y0, y1, y2, y3, and y4. And then I can easily read this off. It's minus y0 plus y1. So minus 1, 1, and everything else is 0. So there'll be 3 more zeros. Then we have 0.99 y1 plus y2. So 0 here. 1, 0, 0. Then 0, 0, 0, 0, 0. And then 0, 0, 0, 0 should be minus 0, 0, 0. Okay, now in this particular case, this is actually kind of, you don't really have to do this extra step of writing this equation. If you see, the last equation actually gives you that you can actually solve for y4 like that. And then once you put that, you can substitute in the first one to get y3 and then y2 and so on. So really, this is an overkill. But I just want to show this to you because in general, you cannot expect that the equation will look as easy as this. But this is normally boiled down to a matrix equation if you're doing, if the problem is linear. So you can solve for y0 all the way to y5, y4, right, by doing ax equals b, so invert a. So this will be a y equals b. So y will be a slash b, though you don't need to do it. Here it's kind of straightforward. You get is y0 is 1.1068, y1 equals 1.1068, y2 equals 1.0958, y3 equals 1.0739, and y4 equals 1.0417. Okay, so you got all these answers, but the answer we were after was y0. Okay, so that's that. So this is what you'll get. You'll get solution not only at time t equals 0 or x equals 0, x0, but also the values of the other time steps.